So if you are in Chemistry 30 and your teachers started with the first unit, which is Thermochem, you might be getting close to writing a unit test, and this review will help you with that. And it's packed full of just old diploma questions. So let's start going through it. So the first one is just a theory question saying the combustion of fossil fuels in a steam plant and cellular respiration are similar in terms of. So the production of energy, absolutely. Production of CO2, yeah. Consumption, yes. And consumption, no. They do not do that. They produce water. So whether we're looking at cellular respiration or the combustion reaction, we know combustion is some sort of hydrocarbon in the presence of oxygen, and that is going to give you carbon dioxide and water. So going through, and it will let off energy. So that's why this first one, your answer is going to be A, because the only one that's not true is this last one, because you're not consuming water, you're producing it. This next couple, we are taking a look at this reaction that's given here. And in the question, it says if 4.50 grams of ethanol was produced according to the above reaction, the amount of energy transferred would be. So this is the formula NH equals delta H. Now, that being energy transferring, you are finding this delta H. This H is the molar enthalpy from the reaction. So it gets confusing because it doesn't have a delta in front of it, but it's the delta H from the reaction per mole of what it's asking about. So in this case, it's ethanol, and ethanol would be this one here. So per 6 moles. So when you go to fill this in, we would start by getting to moles. So to get to moles, you would have, I'm going to start over here, 4.50 grams. We need to multiply by the molar mass of 1 mole of ethanol, which is 46.08 grams. So that step gets grams to cancel. And then you multiply by the enthalpy of the reaction per mole of what it's asking about. So that would be negative 206.7 kilojoules divided by the 6 moles of ethanol. So now moles cancel. Plug that into your calculator and you're going to get negative 3.36, and that's in kilojoules. And if you are struggling filling in numerical response, you get 3 decimals, get a box, and then 3/6. You always start at the left hand side, and you can keep boxes empty if we have to. And then I try and tell kids to get into the habit of always filling in your bubbles, because when you get marked from the diploma, it's going to read the Scantron. Now the next part, talking about the fermentation of glucose, which is what this reaction is referring to. Talking about this one, because you have a negative value, we know it's an exothermic reaction, so you can rule out C and D. And then if it's exothermic, the potential energy diagrams would look like this, where reactants would have more potential energy than the products because it's higher than your products. So when we're looking at it, because it's asking about the reactants are higher. So this one, your answer would be B. So let's move on from here. Our next one, we have about calorimetry. So with this one, you have some information. It is about combustion. Because we have what does it say here? We have the mass of the calorimeter. We have some more information, but essentially this is going to be bomb calorimetry, because they are giving you information of the calorimeter. Oh, that's where it is. Sorry, I should have read this a little bit closer. The calorimeter is aluminum, so that matters because we'll need the specific heat capacity. So when you're looking at bomb calorimetry, the formula is NH equals negative MC delta T, just like it would be for normal calorimetry. But now the container can absorb or gain or release heat, so we need to take that into account with another negative MC delta T. So this question is asking you the molar enthalpy of combustion of ethanol. So we want our left hand side here to be about the reaction of ethanol. So we are going to figure out how much ethanol is reacting by taking the difference between the final mass and the initial mass of ethanol, because then we know how much was reacting, and that was 0.62 grams. Within our formula, we are solving for H, so we'll want that. our first negative MC delta T is going to be about the water. The second MC delta T is about the container, and in this case it's aluminum. So when we go to fill this in, let's just start. We'll have 0.62 grams. We'll need to multiply this by the molar mass of ethanol, which is 46.08 grams per 1 mole. Then we'll multiply this by H, and that will equal, so this first part gets us to moles, so now we're there. So that will equal negative M, so the mass of the water. To get that, we're just going to have to take the difference between these two values, because we have the mass of the calorimeter with water, and if we have the mass of just the calorimeter, if we take that away, we'll know the mass of the water. So it's 250 grams times 4.19 joules per gram degree Celsius times the temperature change. And we have that temperature change here, so final minus initial is 26.6 degrees Celsius. Now we have to add on the negative MC delta T about the container. So the mass of the container is 43.35 grams. We need to multiply that by the specific heat capacity of aluminum, which is 8.97 joules per gram degree Celsius, and still multiply by that same temperature change that was given. Now, this this specific heat capacity can be found on page 3 of your data booklet, and if you can't find it on page 3, it needs to be given to you. Now this right hand side, even though it looks messy, it is just a number, so you can plug this part into your calculator and then add on this part, just keep that in brackets, then isolate H by dividing by your moles. When you're done, you should see that H equals a pretty big number in joules, and because you want it in kilojoules, just divide it by 1,000 one more time, and you'll get negative 2,147.7 kilojoules. Now, a lot of the times you will see this format for answering questions where you'll need to turn it into scientific notation. So I'll have 2.15 times 10 to the power of 3, and then fill it into the boxes. So the 2 would be your A, the 1 would be your B, 5 would be your C, and your exponent would be your D. So this would be 2, 1, 5, 3 when we're filling it in this format. Okay, number 5 here, asking the enthalpy change for the reaction given. Some of these values, because this is not in your data booklet for the enthalpy of the reaction, we have to use Hess's law short. So delta H of your reaction is going to equal the sum of all the products minus the reactants. So when we're looking at this one, we have the reaction given, so we'll start to look this up. If you take a look at this first compound here, methanol, it's negative 239.2, and I'm getting these values from page 4 or 5 of the data booklet. An element by itself is just 0. This one here is going to be negative 425.0, and water as a gas is negative 241.8. You probably should check, because there's no coefficients, if this is balanced, because if it's not, we'll still have to balance it and then multiply by the coefficient in front, but this is balanced, so we can go straight to this formula here, getting the sum of the products and then taking away the sum of the reactants, and in this case you'll get A as your answer. Number 6, here we have the amount of energy involved in increasing the temperature of a certain amount of water by this amount in degrees Celsius. If you're just heating and cooling a substance, it's just that simpler formula, Q equals MC delta T. And you also want to remember that with water, 1 milliliter will equal 1 gram. Oh wait, it gave it in mass. Never mind, we don't even need this time. So we have it in kilograms, but mass should be in grams. So you'll multiply that by 2,000. So Q will equal 2,000 grams times 4.19 joules per gram degree Celsius. Again, you're going to memorize this. If you haven't yet, you can also find it on page 3 of your data booklet, times the temperature change. Now this gives you a pretty large number, and once again that value is going to be in joules, so we'll divide it by 1,000 to turn it into kilojoules, and we're getting that number 32.6 kilojoules. So filling that in, 32.6, and then just make sure you're always practicing when you're doing your tests to make sure to fill in the box so you get in the habit and you don't miss it. Number 7, looking for the molar enthalpy. For the standard enthalpy of formation for this compound here, if it's a formation reaction, you always form from your elements. So you'd have sodium solid plus chlorine gas, which is diatomic, so Cl2, plus oxygen gas, which is also diatomic, so O2, to give you NaClO3. Now, when you're looking at enthalpies of formation, it's usually for just 1 mole. So with balancing, we'll end up having a couple fractions in here so that it's all balanced. Oh, this should have been 3/2. And if we didn't do that, we might have some larger numbers. We just have to make sure that our formation values align. So when we do this correctly, we'll see the answer is B. And I just want to point out a couple, especially that first distractor. This one might look like it's going to be right, but it won't be, because anytime you're looking at formation, you have to form from the elements. So we should not have a compound. So we could rule that one out right away. You can also rule out this one right away because they didn't write chlorine and oxygen right, and then go from there. All right, so moving on to this enthalpy diagram where we have our reactants at -8.38 and your products at -1.25. Sorry again. So when we're looking at this, your enthalpy is always between reactants and products. So that's where we find your delta H. So we're just going to take the difference. And in this case, it is 7.13. And then again, filling this in, 7.13, filling in our boxes. All right, number 9. So with this, given the reaction, we want to figure out the enthalpy change for the next reaction. So notice it is essentially the same reaction, except we have a different factor. So when we're looking, what am I looking at here? When I'm looking at this one, I can recognize that I can get this value, and I actually don't have my data booklet with me right now, but this, oh, never mind, it's right in here. Delta H is going to equal positive 68 kilojoules for this enthalpy. So with this one, we just want to recognize that it's the same reaction, just with different coefficients. So to get from this reaction to the second, we had to multiply by a value of 3/2. If you're multiplying to change your coefficients, you must also multiply your enthalpy, and our value is going to be C. And just to also emphasize that positive, if it was on the reactant side and we take it out and it's endothermic, it's going to be positive. If it was on the product side, then we would have that negative. So number 10, figuring out the enthalpy of combustion of octane, which is given here, and then asked how much energy is produced when 20 grams of oxygen is consumed. So because it's asking about oxygen, we need to know how many moles of oxygen would be formed in this. So we do actually need a balanced chemical equation. So octane, and if you're not sure what this is, you can look it up on page 4 or 5 of your data booklet, is C8H18. And we're going to combust it. So that means reacting it with oxygen, and it will form carbon dioxide and water. Now, it doesn't say if we're in an open or closed system, so you can assume it's liquid water, carbon dioxide's a gas, and we can go from there. Now, we want to go ahead and balance this, and I'm going to balance using a fraction just so that I can keep this as 1. So I would put a 9 here, an 8 here, and then that would give me a total of 25 oxygen on the right. So over here, 25/2 would give me 25 oxygen on the left. Okay, so that's my first step, because I do need to know my moles of oxygen because it's asking about oxygen. So now I'm going to be using the formula NH equals delta H. It's asking how much energy would be produced. So we're looking for delta H, and this value, the enthalpy of the reaction, is going to go in for H, but it is a molar enthalpy, so we have to divide by the amount of moles. So starting with moles of oxygen, we need to get moles of oxygen by multiplying by the molar mass of oxygen. So now we're at moles, And then we can multiply by the molar enthalpy of the reaction, but you have to divide by the amount of moles of oxygen within that reaction. So this 25/2 is going to be very important. We don't want to miss it. Once we do that and plug it into our calculator, and hopefully we did it right, we should see the answer is C. Okay, number 11, asking about this potential energy diagram of all the hydrogen halide compounds, which ones it could be, or sorry, which one wouldn't represent that. What we want to look at is that this, because it's that drop, is an exothermic reaction. So when you go through your data booklet on page 4 or 5, because it's about enthalpies of formation, which page 4 or 5 represents, if you look up hydrogen fluoride, it has a negative enthalpy. Hydrogen bromide and hydrogen chloride are also negative. Hydrogen iodide is the only one that's positive. So hydrogen iodide, being endothermic, would have a different shape. So this one is D. A, B, and C are all represented by that diagram. Number 12, asking about activation energy of the reverse reaction. Reverse means you're starting at your products, and activation energy goes from products of the reverse to the top of the hill. So that's where our activation energy for the reverse is, and we want that distance. So if we just take the distance between 250 and 100, we'll see that the activation energy is 150. Okay, keep going here. This one gives us some information about a reaction. And now this question I do think is kind of mean, but you do see questions like this, so just be aware. This is giving you the reaction with a delta H, so when you take it out of the formula, it's going to be negative. It's an exothermic reaction. But what we want to see is that this reaction is representing decomposition, but then the question is asking you for formation. So if we were to flip the reaction so it resembles a formation reaction, instead of having a negative value, we have a positive value. So that's our first part, is that we're going to have positive because it's saying formation. So we have to recognize that. And then we also have to remember that if it's molar enthalpy, you have to divide by the amount of moles that that value represents. So we're going to divide by 2, and the answer will be C. Now with the next number 14, when it's asking energy involved when we are decomposing. So with this one, this is an NH equals delta H question. We're able to get to moles. We have the H from the reaction, and we're going to find out the energy produced. So we'll have 86 grams times the molar mass of our NaN3, which is 65.02. We're going to multiply this by your molar enthalpy, so negative 43.5 kilojoules, which represents 2 moles of what's reacting. We'll plug it all in, and you get negative 28.8. So filling that in. And then in these types of questions, a common question I get is, how do I put in the negative? Well, you don't. So saying about the energy involved, we know the value. We know it's exothermic. The negative would be implied. Okay, this one about catalysts. Again, some information. Sometimes it matters. A lot of the times it doesn't. So go straight to reading the question. So which of the following potential energy diagrams represents both the catalyzed and uncatalyzed reactions for this process? Now, all catalysts do is lower activation energy. It doesn't change delta H. So this cannot be right because delta H is changing. This cannot be right because it's not changing reactants. Now these two, there are a possibility. So just going through this, oh, actually this is not a possibility because this is showing endothermic. And from what our little bit of information that does show, it does talk about, where is it? A little in this process. No. the products of this process. So this products part is telling us that this is a combustion reaction. And so if it is combustion, we are looking for that XO graph. So it's not this one for that reason. It's not A or C because of how it affected the reactants and the products. It's only D because D has that activation energy and the catalyst lowered it. And that's what catalysts do. Okay, moving on from there. When propane is burned in a barbecue, the molar enthalpy of the reaction is. So propane would be C3H8. Again, if you're not sure, page 4 or 5 of your data booklet. We're reacting it with oxygen to produce carbon dioxide. And if you're in a barbecue and you kind of picture it, there are some holes in there to let the gas escape. So water can escape as a gas. Then we're going to go ahead and balance this. So we'll need a 4 here, a 3 here, and it ends up being a 5 for oxygen. And then because it's asking for molar enthalpy, we are using Hess's law short. So again, that's delta H of your reaction is your sum of your products minus your reactants. Now you could write this formula out a little bit more expanded, but that's how I write it, just to simplify it and make it a bit faster. So I would look up each of these values on page 4 or 5 of my data booklet. O2 wouldn't be on there because it's an element by itself, so we just want to remember that's 0. We'll have 3 carbon dioxide molecules, each with a enthalpy of formation, and 4 water molecules as a gas. So when you're looking at water, just be careful because you do also have liquid water present. So just make sure you're picking the right one. Once you're at this point, get the sum of the products and then the sum of the reactants and take the difference. And you should see here your answer is D. Now, moving on from here, and with the hopes that we have number 16 correct, and it does have this little note here, so it would be still marked. We do want to figure out the amount of energy released. So in an NH equals delta H question, energy released is delta H. We can find N from grams. We have H from the previous question, and then we can keep going. So 425 grams of propane multiplied by the molar mass of propane, which is 44.11, gets you to moles. Now multiply by the molar enthalpy from the previous question, which is negative 2043.9 kilojoules. And that reaction does represent 1 mole. So this number in the bottom would just be 1. Then we want to plug this in. You're getting a fairly large number in kilojoules, but we want it in megajoules. So just divide it by 1,000 and you will see 20.0 megajoules as your answer. Again, make sure you're filling it in correctly, double checking sig digs and your units. Number 18 is another Hess's law short. So filling that in, you're just using, again, page 4 or 5 to get those enthalpies. So FeO would be negative 272. Carbon monoxide is negative 110.5. Iron by itself is just 0. And carbon dioxide is negative 393.5. So I would just double check because there's no coefficients if this is balanced, which it is. So we can move on going back to the formula that delta H of the reaction is your sum of your products minus reactants. So we'll get the sum here for products, sum here for reactants, take the difference, and you should see here your answer is D. Okay. All right, so our next one, we have a reaction given to us with the delta H, and it tells us during the combustion of ethine, energy is blank. So combustion is always exothermic, so it would be released to its surroundings. And if we were to write this within the equation, exothermic reactions go on the product side. So this answer is just theory, and it is B. This one here, we have 5.2 grams of magnesium chloride dissolving in water, and the temperature changes. The enthalpy of the reaction. Because this is going into water, this is a calorimetry question, so you're using your formula NH equals negative MC delta T. Magnesium chloride, so Mg has a positive 2 charge, chlorine negative, so swap and drop. That matters to get to moles. So we'll have 5.2 grams times grams per 1 mole of magnesium chloride. So if I add that up, it is 95.4 grams. And then I'm going to multiply this by H. That's what I'm going to be solving for. And that's going to equal negative 200 grams. And in this one, we can remember 1 mil of water equals 1 gram. So you can just change your units to grams, times 4.19 joules per gram degree Celsius, times your temperature change. Once you're done setting it up, you want to solve for H. So get your total on the right, divide by your amount of moles on the left, and then remembering with your units, everything will cancel out except joules. So your H value will be fairly large in joules, but then when we look at our units of the answer, it's in kilojoules. So just divide by 1,000 to get there. And if you do that correctly, you should see the answer is A. Looking at question 21, we have another enthalpy diagram showing also your activation energy. So this one, going through the difference in potential energy between the reactants and products, is called blank. And the diagram above, it is the difference between blank. So if we're looking for the difference between reactants and products, would be this distance here. That is showing your delta H value. So that would be enthalpy. If it was activation energy, it would be here to the top of the hill. So this time it's delta H, and then saying the difference between, it will be the difference between 3 and 1. So here the answer is B. Number 22 here, we have a reaction. Looking through the reaction, we just want to realize that if it's on the product side, it's an exothermic reaction. So starting off with, if the reaction represented by the equation above, energy is released. So not the first two because it's exothermic. And then the bonds, talking about the bonds, if it's exothermic, just again, quick potential energy diagram, reactants have more potential energy than your products. We also can just get rid of kinetic, because kinetic has to do with heating or cooling, right? You have something moving slower or faster, it's not a reaction. So it does have to have potential in there. So here the only option will be C. Okay. Number 23, we're starting to talk about catalysts once again. So this is a catalyst on the top, and then it's asking about the enthalpy change. And your enthalpy change is delta H. No matter what a catalyst does, it doesn't affect delta H. It just speeds up your reaction, lowers activation energy. So in this case, your enthalpy change will not change. It stays the same because it has nothing to do with activation energy. Number 24, we have another Hess's law short. So just going through it, if we need to, you have 2 moles of butane. So getting that value from page 4 or 5 of your data booklet. And you have 13 moles of oxygen, but we know that that's just going to be 0. 8 moles of carbon dioxide. And 10 moles of water. Negative 241.8. Then again, Hess's law short, take your products, subtract your reactants. So let's get the total here. That will be products. Get the total here. That will be reactants. Take the difference. You should see your answer is C. Okay, now we have a question that mimics a lab, and you probably would have done this lab in your class because it's quite common. So in this one, you have a piece of magnesium ribbon. It's reacting with HCl. In a calorimeter. So we are using the formula NH equals negative MC delta T. The left-hand side is about the reaction. It's asking for the molar enthalpy of the molar enthalpy of the reaction for hydrochloric acid in the calorimeter. So we're looking for H. Now, in this question, we don't have any information about the acid, which is where I wanted to start because it says HCl. So because we don't have information, but we do have about the magnesium, we'll start there. So the magnesium is 0.500 grams. We want to multiply this by the molar mass of magnesium, which is 24.31. We're solving for H, and that will equal the mass of the water. And if you don't have water, because of this aqueous value, we assume that that is going to be the same. We also assume that this right-hand side is all about water, so we still use the specific heat capacity of water. And then this difference gives us our temperature change. So 2.5 degrees Celsius. So just not fitting there. We want to isolate H. When we're done, based on our units, everything will cancel except joules. So we'll get a big number in joules, get that big number in your calculator, divide it by 1,000, and you'll get 50.9 kilojoules per mole. So 50.9. And again, get in that habit of always filling in your boxes so that you don't forget. Okay. Question 26 gives you some information. So we're using this text box. If you have a delta H that is negative, we know from a potential energy diagram that it would look something like that. Now it's also giving you the activation energy of the forward reaction, and that is always from the reactants to the top of a hill. So we're going to just draw in a hill. So it will look more, let's draw it a little bit nicer, like that. Okay, so this distance between the reactants and products is your delta H, and that's negative 40. This distance between your reactants to the top of the hill is a distance of 30. So asking the activation energy of the reverse reaction, that is from your products to the top of the hill. So when you're looking at that, don't worry about the negative. Just, we want this whole distance. If we know part of the way is 40 and the rest is 30, just add those values together and we're going to have the total 70. If it's asking you about the enthalpy change of the reverse reaction, if you know that delta H is negative 40 kilojoules, then we reverse it, you just flip your sign. So we're not trying to trick you here, just know that enthalpy, you flip your sign. So that would be C. And then the last one, a catalyst speeds up the rate of the reaction by. It has no effect on delta H. All it does is decreases the activation energy. If it increased the activation energy, it would mean that the reaction takes even longer. So if that hill lowers, it's faster. 29, I think kids that take bio are good at this one. So number 29, saying what a catalyst is. It's not consumed in the reaction because it's not part of the reaction. It's not produced because of the same reason. It's not necessarily unchanged during the reaction, so it can change and then change back. But the best answer is D. It's regenerated at the end of the reaction. So this is a bit of a theory question and it gets a little harder. So just make sure that you can even rule out the rest. Again, if you're taking bio, you probably would have gotten it anyway. This next question, number 30, this is showing us Hess's law long or mathematical. When we're doing this question, we want to look at our target and try and rearrange our known equations to get to the target and see how we can add our delta H's to get there. So I'm going to start with aluminum. I think so far, this first one, it's where I need it. So I'll just write it down how I see it. I'm not changing anything. So I'll just copy it exactly. Okay, so I haven't changed this one. It's remaining the same. I'm not sure what I have to do with this one yet, so I'll look in a second. Because it's changing the states, I'm pretty sure this means that my states of HCl are going to matter. Now, this next one shows me Cl2, and it's a reactant. And this one here, it's also a reactant, but there's 3 of them. So I'm going to take this whole reaction and multiply it by 3. But when I do this, I have to remember that also multiplies the delta H by 3. So I have now 3H2 plus 3Cl2 to give me 3 times 2 would be 6HCl gas. And that's, we'll get to it in a moment. This next one, this last one, AlCl3 solid, and then also as an aqueous, which now also tells me I should really be putting that state in as well. So this last one is showing me what I need. I need the solid state of AlCl3, and in this target, my solids on the reactant side. So I'm going to flip that reaction and have the aqueous first, and then AlCl3 solid is on the product side now. And because I flipped it, this reaction is now positive. So positive 323.0. Okay, so then the last one I have to deal with is HCl aqueous. So notice we don't have HCl in the equation, so we need to get it to cancel. So to cancel it, I need HCl aqueous on the product side and the gas on the reactant side. I also need 6 of them. So coming to the my manipulated equations, I do have what I need on the correct side, but I don't have enough. So I'm going to multiply all of these by 6. So I'll have 6HCl, which one was first? Gas, and 6HCl AQ. So now everything is where I need it. You should see things canceling wonderfully. Aqueous, aqueous, H2, H2, and then you should be left with your target, which we are Al, 2Al, which we have, 3Cl2, which we have, and our last one, oh, I missed that. That needs to be multiplied by 2, which makes sense because we need it to cancel. So multiply this by 2, which means this last reaction, not that one, yes, that one, needs to also be multiplied by 2, not just flipping the signs. Okay, now it will cancel nicely. So now I can cancel that, and I'm left with what I need, that 2. And I've accounted for it in the delta H. So I have everything I need. Now my last step, and the one I actually need, is paying attention to all my delta H's and how I manipulate it and add them all together. So starting with the first negative, and then the second one multiplied by 6, the third one multiplied by 3, and the last one we flipped that sign and multiplied it by 2. Adding it all together, we'll see that answer is A. Okay. Almost at the end here, number 31. Asking which of the following potential energy diagrams represents a reaction where delta H is positive 50 and the activation energy of the reverse reaction is 30. So when I would look at first here, if you have a delta H that's positive 50, you are endothermic. And if it's endothermic, your reactants are lower than the products. So you can cross out B and D. And then unfortunately with this question, A and C have to be accepted because we have no scale. So the activation energy of the reverse reaction, we really don't know if this one is 30 or if this one is 30, because again, we have no scale. So at this point, I would have to say A and C are accepted. And I'm not sure if this is just a typo from everything getting like formatted and it's just missing, or if that's how it was. If there was a scale, we should be able to pare this down even more. Okay, the last 2 questions here. We do have another Hess's law short. So just doing that quickly, delta H is going to be products minus reactants. So 0 here, 2 times HCl, negative 92.3. Here, 2 times HBr is 2 times negative 36.3. Chlorine is 0. The sum of the products is just this. Sum of the reactants is just this. Take the difference, and you get positive 112. So 1, 1, 2, and this would be a good example of showing how you don't fill in the last one. So if you were tempted in this numeric response to put, say, a 0 because it's empty, you now have the question wrong. So don't do that. Boxes can stay empty. And now this very, very last one is another Hess's law long or mathematical, and it doesn't give us our target, so we're going to have to come up with it ourselves. And if you are a formation reaction, what this is implying with that little f, then it means this compound was formed from its elements. So we'd have carbon by itself, plus oxygen by itself, plus hydrogen by itself, to give you HC2H3O2. And then you'd have to balance this. So we'll need a 2 here and a 2 here. So the target equation here wasn't given to you, but we can come up with it. Now we're going to manipulate your known equations to get to this point. So when I'm taking a look at this, I'm going to start with that first reaction, and I have my formation of acetic acid on the reactant side. I need it on the product side. I'm going to flip that reaction. So I'll have 2CO2 plus 2H2O to give me 2O2 plus HC2H3O2. Because I flipped this reaction, I am going to change my sign. My next one, I'm fine with where I'm seeing my carbon because I need it as a reactant, but I do need 2 moles. So I'll need to multiply this reaction by 2, which means I multiply my delta H by 2. So I'll have 2 carbon plus 2 O2 to give me 2 carbon dioxide molecules, and then my delta H will be 2 times negative 394.51. My last one, I have my hydrogens, my oxygen, and water as a liquid. And in this case, when I'm taking a look at what I need, I want my hydrogen to be on the reactant side. So it is where I need it, but same as the previous one, I need 2 moles, and this is only showing me 1. So I'm going to take this whole reaction, multiply it by 2, and write it down. So 2H2 plus 2 times a half is just 1, so O2. Then we have the other side would be 2 water molecules, and then this delta H is going to be 2 times 285.8. So now before we add up our enthalpies, we just want to make sure that everything crosses out and we get our target. So we'll see carbon dioxide canceling, you'll see water canceling, you'll see 2 of these oxygen canceling, and is anything else canceling? No. So we're left with 2C, which we need, 1 oxygen, which we need, 2 hydrogens, and then our product information. So we're confident now that we've done it right. Now we can add up our enthalpies and just plug it into the calculator, and you should see your answer is B. So as always, I hope you found this helpful. If you made it all the way to the end and you have a test coming up, best of luck to you. And if this was helpful, I would appreciate it if you can subscribe. And if there's any other video I can do for you, just let me know. Thanks for watching. Go down.